we have different rules of exponents. The rules of exponents that we use most frequently are the product property, the quotient property, and the power property. We almost use them without thinking about it a lot of the times. Our product property tells us if we're multiplying two powers, we can add our exponents. When we have something like a to the fourth times a squared, think of it this way. If it's a times a times a times a, that's a to the fourth, right? And a squared is a times a. This is why we can add our exponents, because we have 4 and 2 more, we put it together, and we have a to the sixth. Okay? So we can add our exponents when we are multiplying powers. The quotient property tells us if we are dividing, we can subtract the exponents. So if I have a cubed over a squared, that's a times a times a divided by a times a. Well, a divided by a is 1, right? So that's 1, and that's 1, and so I'm just left with a to the 1 power, which is what I get when I subtract my exponents, 3 minus 2. Okay? So the rules are shortcuts to writing it all out. And this is something that you've been doing like every year in math since like 6th grade. Because my kids are in 6th and 7th grade, and I've seen them work on exponent rules. Okay? But it's about reminding you and refreshing your memories. So then the power to the power property says when I raise a power to a power, I can multiply my exponents. So if I have a squared to the fourth, that means a squared times a squared times a squared times a squared, which 2 plus 2 plus 2 plus 2 is 8, and we get the same thing if we were to multiply 4 times the 2. Okay? So that's a little bit as to why the rules work. Okay? Then we have the 0 property, power of 0 property. Any base with a 0 power equals 1. That's because if I have a to the 7th divided by a to the 7th, if I subtract my exponents, I get 0, right? But anything divided by itself is what? 1. So a to the 7th divided by a to the 7th is equal to 1, which is why a to the 0 is equal to 1, because it represents dividing something by itself. And then the one that gets us the most, we have the most trouble with, is the negative exponent property. It says a to the negative m is equal to 1 over a to the m. And so here's my explanation on that. Like, why does the negative exponent mean it goes in the denominator? Well, if I have a to the fourth divided by a to the sixth, if I subtract my exponents, I get what? Negative 2, right? 4 minus 6 is negative 2. If I write it out and cancel them, these all equal 1, and I end up with 1 over a squared. So that's why a to the negative 2 is equal to 1 over a squared, because it represents having more of that in the denominator. Okay, there's more in the denominator, and so the a squared has to stay there. And then the other part of the negative exponent property is the negative exponent really means reciprocal as well. So if you have a fraction, it can flips the fraction over. So if I have 3 halves to the negative 1 power, well, the inverse and reciprocal of that is 2/3 to the positive 1. So the negative exponent makes a reciprocal of a fraction, or puts the exponent in the denominator and makes it positive. So those are our rules and quick explanations as to why they are what they are. Now, I apologize for this really strange numbering. I don't know what happens to Mrs. Whip's computer when she hits the button save. It changes all the numbers. Like, so she originally wrote it with 1, 2, 3, 4. It doesn't shuffle the problems around. It just changes the numbers for her. So we didn't purposely start with number 8 and then go to 4 and 5 and 3 and 6. I mean, it's like there's no rhyme or reason on this worksheet. I don't even know. Okay, So we're going to start with number 8 here. Negative 2 to the 4th. And this is 1 and 2. So we're going to go up and down. What is the difference between what we see in problems number 1 and problem number 2? Right. Number 2 doesn't have parentheses. And the parentheses are really important. The parentheses tell us whether the negative is getting repeated or not. So in number 1, negative 2 in parentheses to the 4th power means it's negative 2 times negative 2 times negative 2 times negative 2. The negative is getting repeated, okay? So we're going to write that out, which is a positive 16. Now you don't have to write it out every time. It's just I want you to understand the difference in what they mean. So negative 2 to the 4th in number 2 looks like this. Negative 2 times 2 times 2 times 2. The negative is not getting repeated because it's not in the parentheses. Okay? So that answer becomes negative 16. So number 4, or technically number 3, is the negative getting repeated in number 4 here? Yes. So it's negative 2 times negative 2 times negative 2, which is a negative 8. When a negative is raised to an odd power, it stays negative. When a negative is raised to an even power, it changes to a positive. Now number 3, or 4, negative 2 to the negative 3rd power. Remember that the negative exponent doesn't make anything negative. Okay, the negative exponent makes it a fraction. And that negative is inside the parentheses with the 2, so it's going to go into the denominator with the 2. So this is rewritten as 1 over negative 2 cubed. That took away the negative exponent, the negative in the exponent, by making it a fraction. And then I can evaluate it 1 over negative 8. Because negative 2 times negative 2 is positive. 4 times a negative 2 gives us a negative 8. Yes. Unless there's something, unless there's a coefficient, like when we get to number 12, it's not going to be a 1. It's going to be a 2, but we'll get there. If it's just a number to a negative exponent, it's 1 over. Okay. Because remember that you can write it as a fraction, negative 2 over 1, and then do the reciprocal. Number 5. Negative on the outside, there's no parentheses, 2 to the negative 3. So that's negative 1 over 2 cubed, which is also negative 1/8. With the odd exponents, where the negative is doesn't really make a difference. Yeah.
So if there's no parentheses around like the negative 2, then you get parentheses at the 1, or like on the outside of the column?
Yes. And number 6, 2/3 to the negative 2. So the negative exponent makes it a reciprocal, and then we'll raise the top and the bottom to the 2nd power. So I get 3/2 squared. That's what the negative did. It flipped the fraction. And then 3 squared is 9, and 2 squared is 4. Okay, so then 7 and 8, 0 to any power is 0. So these are both 0, whether there's parentheses or not. Now, what about 9,432 to the 0 power? That equals 1. Okay. Doesn't matter how crazy the expression is inside the parentheses. If it's to the 0 power, it just equals 1. And then we'll do 9, 10, 11, and 12. Okay. Now, looking at 9 and 10, yes, the exponents have different numbers, but what is the biggest difference between the two? The number 10 has parentheses, number 9 doesn't, right? So just like the parentheses around the negative, right? When the parentheses are around the negative, that means that negative is getting repeated. If the parentheses are around a coefficient, that means the coefficient is being repeated. So that means the number 9, the coefficient 2, is not getting repeated with the exponent. So it's really two separate things, 2 times x to the negative 3. X to the negative 3 is 1 over x cubed. And we can write that as 2 over x cubed, because we can multiply the 2 times the 1 in the numerator. Now, what I've written below the problem does not have to be shown as work. We need to get to the point where we see 2x to the negative 3 and we realize the 2 is not being repeated, so it's in the numerator, and the x cubed goes in the bottom because it's negative. Okay. Now, number 10 is a little different because the 2 is in the parentheses. So the numerator is 1, and the 2x squared is in the bottom. And can I do 2x squared? Can I evaluate that? Right, 4x to the second power. Okay, so in number 11 and 12, they kind of have a lot going on, and we have options. Okay, we can choose to move the negatives around and then simplify each variable separately. We can choose to simplify each variable and then deal with the negatives. It doesn't really matter which way you choose. Okay, so you have to decide which method you think makes more sense to you. Okay, so I'm going to show you 2 ways to do number 11. All right, the first way is to first deal with the fact that we have a bunch of negative exponents everywhere. Okay, and if a negative exponent is in the denominator, that moves the expression to the top and makes it positive. And if the exponent is negative and it's in the numerator, it moves it down. So this expression becomes, now these are our numbers. These don't change anything. It's just negative 2/3, right? So I have negative 2 in the numerator and 3 in the denominator. My a to the negative 3 is going to move up and become a to the positive 3, and my a to the negative 1 is going to move down and become a to the positive 1. So I'm just moving them up or down. If they're negative, in the top they go down, bottom they go up. The positive, the b squared, is going to stay on top because it's positive. And the negative, the b to the negative 4 on the bottom, is going to move up. So b to the positive 4. To simplify an expression, I should only have one of each variable. So I need to simplify it so I only have one a and one b. Use my quotient property to subtract my exponents for the a. So what do I get? A squared, 3 minus 1. And b to the second times b to the fourth. Multiply to get b to the sixth. Sorry, add to get b to the sixth. Okay, so the alternate way, show you I get the same answer. I start with my negative 2/3 and I subtract my exponents. So on the a, I have negative 1 minus negative 3. What's negative 1 minus negative 3? Plus positive becomes a squared, right? 2. Is that what I got on the first way we did it? Yes. And then b to the 2 minus negative 4. The quotient property says we subtract our exponents, but we have to really pay attention to subtracting negatives. So we end up with b to the 6th. Which one? This, it was negative 1 minus negative 3, right? Became plus positive. So it was originally better? Okay. So which way do you like better? Because we'll use that way for number 12. The first one? Okay. Okay, so for number 12, we kind of have even more going on. We have that exponent on the end. So what I like to do is simplify the inside of the parentheses and then worry about the exponent on the outside. So I'm going to rewrite. We said rewriting the exponents as positive is what you liked. So is that correct? The negative 5, x to the negative 5, moved up and became a positive 5. The y to the negative 3 moved down and became positive 3. I'm not done. Now I can simplify my x's. X squared times x to the 5th is what? Right, x to the 7th over 4y cubed. And that's all to the negative 6th power. Now let's deal with the negative, which flips the whole thing around, makes it a positive 6. So the negative exponent on a big complicated fraction just flips the whole thing around. Now I'm going to raise everything to the 6th power. 4 to the 6th. Power to a power, what do we do with our exponents? Multiply, so at 18 over x to the 42. Generally, 4 to the 6th is pretty big. You can do it in your calculator. You get 4096, y to the 18th, x to the 42. Usually on tests and quizzes, we keep the numbers small enough for you to evaluate without a calculator. Like 4 squared, 2 to the 4th. All right, so let's look at number 21. Again, you could rewrite it without the negative, or you can use the rule first and then deal with the negative at the end. Okay. On these, I tend to just add the exponents together. What do we get? Negative 9 plus 2 plus 4 is negative 5. So I get 2 to the negative 5. Which is 1 over 2 to the 5th, which is 1 over 32. Let's go down. We're going to do these three, 21, 20, and 22, and then we'll go over and do 19 and 18. Okay. So number 20, what do you think we get? What do you think we do? Let's look at the basics. Ignore the exponents and the variables. We got to do 2 times negative 3. What we do with the numbers doesn't change because we have exponent rules. They're not exponents. So I get what? Negative 6. And what's the exponent on that second x? Remember, it's a 1. So when I add my exponents, negative 8 plus 1, I get negative 7. So I get negative 6x to the negative 7th, and we never leave negative exponents in our answer. So that's going to become negative 6 over x to the positive 7. Number 20 here, or 13, whichever you want to call it. This would be 13, 14, and 15. We have to kind of separate this into two parts. Okay? We have to do this part first, and then we can multiply it by the blue part. The order of operations still applies, really. We have to do that exponent, and then we can multiply it by what's in front. So on these ones, I usually tend to just distribute my exponent and deal with the negatives on the end. Now, if you don't like to do it that way, you can rewrite it without the negative exponents and do that step by step. Right? There isn't one right method. Okay? So that gives me x to the negative 15, y to the positive 6. Because we multiply our exponents when we raise a power to a power. That we're multiplying by 2x squared, y to the negative 6. Now I can write this with positive exponents. 2x squared over y to the 6th times y to the 6th over x to the 15th. So all I did was move my negative exponents into the denominators. And now I can simplify. Does anything cancel out completely? The y to the 6th. Y to the 6th divided by y to the 6th is 1. I get y to the 0. Then if I subtract my exponents on the x, I get what? It's 2 over x to the 13th, because I have 2 minus 15 as my exponents. Negative 13 means the x will go in the denominator. Okay. 4, 15. We'll call this 16 and 17. Okay. Number 16. 7 squared divided by 7 to the negative 4th power. We subtract our exponents. 7 to the 2 minus negative 4. What do we get? 6. So 7 to the 6th power. My base doesn't change. Okay, one of the biggest mistakes students make is they look at these problems and they go 7 divided by 7 is 1, and they change their base to 1. Or they do number 13 here, and 2 times 2 is 4, so they change their base to 4. But we're talking about powers. We're talking about repeated multiplication of that base, so the base doesn't change when we add our exponents. Okay? When I finally evaluate, then my exponent goes away and I don't have a base, but my base doesn't change when I'm raising it to a power. Okay? Oftentimes we'll put a problem like 9 to the 10th divided by 9 squared. Thinking this is a quick, easy problem, right? Those are easy points. What should we have? What do we get? Nine to the 8th. I don't need you to know what 9 to the 8th is off the top of your head, right? But we should know that's 9 to the 8th. It doesn't become 1 because I'm actually multiplying a bunch of 9s together. And then dividing it by 2 9s, so I'm canceling. Did these change? No, they're still 9s, right? And people write the answer as 1 to the 8th all the time. All right, last problem we're going to do today, here number 17. 3x squared y to the negative 3 over 9x to the negative 4 y to the negative 2. So again, treat my numbers the same. 1/3, not 3, 1/3. When the bigger number's in the denominator, it's a fraction. Okay. And then we can subtract our exponents, or you can rearrange it, however you like. Yeah, that's what I'm doing, right? 2 minus -4. What do I get? X to the 6th, right? So that, and then y to the -3 minus -2. So y to the -1, which means y is in the denominator. So when you're doing that subtraction, that simplifying, and you get a negative exponent, you put it in the denominator as a positive. If you get a positive exponent, you put it in the numerator. Okay, let's do it the other way. So we have 3, well, we already know that's 1/3. I have x squared x to the 4th, right? Because the x to the -4 on the bottom will move up. And then the y squared moves up and the y cubed moves down. So we still end up with x to the 6th on the top and 3y in the bottom. And whether I write the 1 in the numerator or not is up to you. Georgia? So I simplified, right? 2 minus 3 is -1. Because remember, that means y times y divided by y times y times y. So 2 of them cancel. Okay. So that's what you're actually doing when you're subtracting them. That's just a shortcut to, oh, we're dividing out all the common ones there.